So in the pieces we were doing Wednesday, we were looking at two groups which may or may not have anything to do with each other. So what if I have samples that clearly do have something to do with each other? The same patient before a treatment or after a treatment for some medical procedure. We measure someone's blood pressure, then they go on a medication, we measure it again. We take the average over 10 readings before, we take the average over 10 readings after, and we look at what changed. Did anything change? I run a machining operation. I have a tool, say a drill press. I have two different lubricants. Which one works better? I run 10 batches of the machine with lubricant 1, measuring the temperature each time. I let it cool off. The next day, I run 10 batches with lubricant 2. I measure temperature each time. But now I clearly have data that's related to the same object in a way. That means I want to pair my data and thus pair my test. So what we really do is we take the difference. Actually, I'm just going to call it D is X1 minus X2, where each set of data is paired. So if I have all of the befores and all of the afters, or I've got the 10 different batches that I ran, I've got readings like this. Our daughters taller than their mothers. So here are the mother's heights, here are the daughter's heights. Take the difference. Is there a statistical measurement here that would tell me, hey, yes, daughters are taller than their mother on average, or not? Or I'm looking at pricing for drugs. Here are 10 different pharmacies, prices for the same dose of 2 different epilepsy drugs. Is one drug markedly higher or lower than the other? You're an athlete. Your coach tells you leave it all on the field, not just during the practices, but during the actual event. So here are the preliminary times and the actual times. Are people faster? The coach says typically they're more than a half second faster than going into the meet. So the actual times are faster than the seed times. Is it true or not? Well, what I do is I pair up all my data and I create this new variable D. And then I can ask, what do I know about this variable? I can do a single t-test on D. And I'll do the same t-test I normally do. Now, if I were going to do this by hand, this would be a lot of long calculation. I'd have to go through and make my new variable, and then I'd have to do all the t-test stuff we were doing before. I don't have to do any of this by hand because in Excel, here's my swimming data. I can tell Excel, hey, what I want you to do is do all the differences automatically. I want you to assume this data is paired. So I'm going to, just like I did before, go into my data analysis, and I'm going to do a paired sample. It's a t-test, but it says right there, paired. I don't have to worry about the variances. It automatically deals with that appropriately. So if I tell it I want to do a paired 2 sample, it asks me what's the first variable. There's my first variable. What's my second variable? There's my second data. Oop, I hit a button again. There. I think the swimmers were on average half a second faster, right? So I'm going to put in 0.5 for a hypothesized difference. And then, yeah, I put the labels in there, and it says at alpha equals 0.05. So I've got the 5 right there. 0.05. Does this work? Let's take a look at what it spits out. Are my swimmers half a second faster or not? Please notice there were 26 swimmers listed, so my degrees of freedom is n-1 because we're just basically doing a one sample test because we paired everything. So DF there is 25. Hypothesized difference was 0.5. I'm going to spread this column out so we can see the labels better. Okay. Again, there are two ways to tell. How do I know whether or not no, there's no difference, or yes, there is a difference? The null hypothesis would be there's no difference. Or in this case, that the difference is less than 0.5. The alternate hypothesis would be that the difference is more than 0.5. What two pieces of information up there tell me what to do? The one tail, because we paired my samples, then I did one calculation on that. So this paired value is 0.0403. What does that mean? It's smaller than my alpha, which was 0.05. I don't need the update right now. Thank you. So that means reject. What's the other way I could have gotten that same information? Mike?
The piece that is more positive than the critical value for one tail.
There we go. The T stat is 1.82. My critical is 1.708. That means we're too far out. We're not. Now this said bigger than, so this was a one tail test. And so I was able to get this directly from there. Close that. Here, let's take a look at the prescription drug comment. Here's my two different prescription drugs, right? Same statement. Now, in this case, the problem asks, is there a difference between the prices of these drugs? So it just asks about a difference. Am I doing a one tail or a two tail? Because it's just asking for difference. Either they're equal or they're not. What's my hypothesized difference? It should be 0. Either they're equal, the difference is 0, or it isn't. So when I go to do that same data test, data analysis, paired test, now I need to change where my data is. So my first one is only this set of data. My second one is only this set of data. I have labels, but now the hypothesized mean difference should be 0. I create the data single value by subtracting, and then I look at the average on that, And my t calculated this time is there a difference between the prices of these two drugs? According to my current sample. Pregabalin versus gabapentin as anti-seizure drugs. That's an important difference to have. So what does this tell me?
P-value for two tails is really big.
The p-value for two-tail is really big. That's right. But what's the alpha in this problem? I didn't actually say. But normally it would be like 0.05 or 0.1 or something, right? It might be really small, like 0.01. But in this case, even if it was like 0.1, that p-value is 0.29. What does that mean?
And you sell every day.
Which means, according to this set of data, the prices are the same. There's not enough evidence here to tell me one of these drugs is significantly priced differently than the other. Maybe I need to check more pharmacies. Maybe I need to look at a larger set of data, but based on this set of 10 samples, no, this data is the same. Now, I was just looking at how to do this on the calculator, and I could not find a paired version of the test on the graphing calculator. So when I'm here in my tests, I'm doing a t-test. And I said to myself, well, if this is a two-sample t-test, I should be looking here. And when I look at this pile, there's nothing in here about pairing my data. If I go to the data itself, it doesn't give me an option to pair it. So in order for me to do this on my graphing calculator, I have to do the work to create D, the differences, and then do the sample. I can still do a t-test, but I'm only doing a one variable t-test, not a two variable t-test, but I have to create the new variable. I have to do this subtraction here and then do the t-test on that. So if I want to do this on the graphing calculator, there's one other step for me to get what I want. That's not to say it's not possible. It's just not what I can do as quickly as I can do it in Excel. Questions? Okay. Means 1, 2, and now paired versus unpaired. What else did we do with our Z and T tests? We did means and we did proportions. So how do I do proportions? With two samples. So again, if I've got two populations, then I can say, all right, what's the proportion of people in group 1 that think this way? What's the proportion of people in group 2 that think this way? I'll have population 1 proportion versus population 2 proportion. Just like I had mean 1 versus mean 2. Okay. Well, now I'm checking a difference. But again, I have a right tail test, a left tail test, and a two tail test. So my null hypothesis could be that the difference between my populations is big, or It's not. It could be that the difference between the populations is 0. Or it's not. It could be that the difference between the populations is less than or equal to 0. Or it's not. Now look at your alternate hypotheses. That tells you which kind of tail test you're looking at. This is a left tail. This is a two tail. And this is a right tail. So, I'm going to end up with the same question I did for the previous version with the means. I need to know, first of all, are the variances equal or not? Can I pool the variances or the gross behavior? So I do the same thing. I gather the sample populations. Sample proportions. You can't have a sample population. It's sticky, pull hard. I can think of this as the same thing as I thought of with the pooled variances. If the proportions are roughly equal, then I can pool the samples. Like our pooled variance. Now, here's an interesting result, though. Remember, the way we calculate our proportion is you take the number of people who did what you want divided by the total number of people. Our pooled version comes from combining the numerators and the denominators separately. That's not just the same as adding the two fractions. That's an important difference. This is called our combined proportion. And it plays the same role as our pooled variance did, meaning the calculation on mean. So I'm going to do a z-test here. If I have a normally distributed idea, then I'm going to do a z-test. Now that's a big if, because I don't know off the top of my head whether or not these are normally distributed. I'll figure out how to check that in a minute, but I need a z-score. So I calculate a z-score. Now for a proportion, I'm going to divide by the standard error. But the standard error here is found using this combined proportion. This is the same standard error we were using to find the confidence interval. Proportion 1 minus the proportion and then 1 over the populations. This makes the assumption that my populations were roughly equal, that the proportion difference, the expected difference between these is 0. That's what I said back here. The expected difference is 0. If I have an expected difference that's not 0, I should be subtracting it. In the textbook, there's this formula, which again assumes that our proportions should be equal here. If it isn't, then we would use a very different looking formula with unpooled variances. There's my expected difference, and here's my unpooled version. I'm not going to use that one in this course. Most of the time, we would say, hey, we expect the proportion of people to be the same in most of our behaviors. We'll talk about the unpooled version in another fashion. All right, again, there are lots of different ways to get at this data. If I'm doing proportions, proportion z-test for 1 and for 2. So here's my 2 proportion z-test right here. So I can go in and I can get all the information. Now notice something interesting here. What's not available to me this time?
You can't use the data.
I can't put in, I have to put in the summary statistics, which means I have to calculate X1, N1, X2, N2. I have to know those numbers. I don't have a way of going back to the data and pulling it up. So in a problem like this one, problem number 23, A, B, or C, pick one. We'll do whichever one you want, A, B, or C. A. Repeat buyers at 2 car dealerships. How many people come back to buy another car? In the first group, there were 50 people and 30% of them came back for another car. In the second group, there were 50 people and 54% of them came back for another car. Is the proportion statistically significantly different? Now, my first reaction is, hey, 30 versus 54, that's a difference, right? But it doesn't actually help me calculate whether or not that distance difference is statistically significant. So I'm going to do this 2 ways. We'll start with the data they gave me. Now, they actually gave me one other piece of information. And they want to know, it says explicitly, a left tail test. All right, wait a minute. What's a left tail test? For a left tail test, what's our null hypothesis? What's our alternate hypothesis? That's why we wrote those down. So I go back and I look and I say, oh, for a left tail test, this. My null hypothesis is that we're okay. We're on the right side. And my alternate hypothesis is that we're on the left side. Now, here's the problem. In order for me to create the information I need for this formula, I need that combined proportion. So I go back up here and I look at how to get that combined proportion. I need the actual number of people, X1 and X2. And I don't have that. How do I get X1? How do I get X2? You don't have to give it to me, just tell me how to get it.
Do like portion times the number.
Aha. Since P is X over N, that means that P times N is X. So to get X1, I multiply P1 by N1, 0.30 times 50 is 15. X2 is P2 times N2, 0.54 times 50 is great. So my combined proportion is 15 plus 27 over 50 plus 50, which is 0.42. Great. Now I can do this. I'm going to do it by hand for the moment. I can do this in the calculator because I have the X and the N in both cases. But I want to walk through this calculation. So, zcalc is P1 minus P2, 0.30 minus 0.54 over square root. Combined proportion, 1 minus combined proportion, 1 over N1 plus 1 over N2. That's the formula on page 385. So let's do the arithmetic. What do we get? Negative 0.24 over the square root of something. I'm just typing in that denominator exactly the way I found it. I get that. Then I take the square root of that. So I take the square root of that, square root of the answer, and then I'm going to take negative 0.24 and divide by that number. Negative 2.43. Now, there are two other pieces of information I need. I need either the p-value for this, or I need a z-critical. Which one do you want to get? A p-value or a critical? Okay, if I'm doing a z-critical, remember that alpha is 0.01. So I need to go to my z table and I need to find either 0.01 or 0.99 in the area. So that's in the middle here. 0.01, 0.001, 0.007. Hey, here we go. Here's some 0.01s. There we go. Negative 2, 3. Let's go with this number. 233. What does that mean? We accept our null, or do we reject it? In that blank, either goes the word reject or the words do not reject. Because right, but it's outside, right? In absolute value, it is bigger. Now, the other way I could do it would be to get the p-value. And the p-value, again, I'd either have to calculate that using my distribution. I want it's a normal, right? I want the inverse normal. The area should be 0.01. There's my Z critical, right? If I want the p-value, I want the normal, I want the CDF. My lower bound is minus infinity, and I go up to negative 2.43. Ooh. The upper is negative 2.43. My p-value is 0.0075. Now, I could actually do that on the table too. I would go to 2.43 on the table. Negative 2.43. There's negative 2.43. It's 0.0075. 0.0075. That's smaller than 0.01. So I reject. Which means, as far as I am concerned, for this set of data, there is a difference. The first car dealership has a lower repeat buyer group than the new second car dealership. I don't know if it's old or new, or if it's just two different dealerships. Questions? Do all that on here. I can do it in Excel. I can do it by hand with my table. Your call. Questions? I made an assumption. Before I did this problem, I wrote right here, if the populations are normally distributed, I can do a z-test. I'm doing proportions. How do I check for normal? By the way, this is the same way we check for normal in any proportion problem. How do I check for normal for any proportion problem?
Is it like successes and failures that have to be more than 10?
Exactly. And this time, since I've got more than one group, I need to check that that's true in both groups. I need to check that it's true in group 1 and in group 2. So in what we were just doing, the example we just did, population 1 was 50 people. How many successes did I have? 15, which means how many failures? Both of those are bigger than 10, I'm happy. Second population was also 50. How many successes? Which means how many failures? Both are bigger than 10, I'm happy. If either the number of successes or the number of failures are too small, or if n itself is too small, then I really can't make my assumptions about being normal. And I have to do something ugly, which is that binomial approximation to a normal distribution. And that's just really, really unpleasant. But that's only done in small groups. And I really need a good software package to do that. I will not do that by hand. I will only do that in Excel. I won't even do that on the calculator because it's a summative binomial calculation. It's several binomial CDF pieces put together. I don't think it's worthwhile to even consider. And all I need to do to make up for it is to do a larger sample. And that's a lot easier to do. Questions? Okay. A t-test and a z-test are flipped up interpretations of a confidence interval, which means I can think of this entire process as something I can do confidence intervals on. Okay. Well, if I've got a confidence interval, I should be able to find it by taking the difference in my populations and then adding or subtracting by the z-value times the standard error. Now, this standard error does not use the pooled proportion, the combined proportion. This uses the separate proportions. So let me go back. to the problem we just did. I'm going to go grab all that information again. Here we go. Here's my information. And they told me alpha was 0.01. With me so far? I want this. Advantage. Where am I going to get that number? I can get it off the table. I can get it off the calculator. I can get it out of Excel. How do I get that number? Harry, you're putting something in your calculator. Tell me what you're doing. Okay. So I grab my table, and what do I look for? It's right in between these two, isn't it? Negative 2.5 between 7 and 8, right? So 2.575. Sound reasonable? I am going to say plus or minus. It says that right in front there. I could do this in Excel. This is a previous calculation I was working on, but let's just pop open Excel. Now I know the area is 0.05. I want the value back. So I say, all right, I need the normal inverse. Inverse, nope, it's norm.in. There it is, normal standard inverse. Normal standard inverse. Oop. And then I have to know what the probability is. 0.005. Negative 2.575. So there's my number. Perfect. I can get it off the calculator using the inverse normal on distribution inverse normal. Negative 2.575. Lots of ways to get this number. So now I put everything in here. 0.30 minus 0.54 plus or minus 2.575 square root of 0.30, 1 minus 0.30 over 50 plus 0.54, 1 minus 0.54 over 50. I'm going to calculate that square root number first. So that's the number under my square root, 0.009168. Take the square root of that, square root of that. Okay, that's the number that goes here. I'm going to write that down. 0.0957496. I'm just a pain in the ass. I write down all my decimal places. You don't have to, you can round off here depending on what you're doing. 2.575 plus or minus, and then 30 minus 54 is negative 0.24. So I'm going to multiply this number by the 2.575, that's here, multiply by 2.575. And I get 2.465. So negative 0.24 plus this number is just barely bigger than 0.0065, and 0.24 minus 0.2465 is negative 0.0065. Please notice how far to the left of zero that is. Not a lot left of zero. I mean, it just barely covers zero. In my result, we rejected the null hypothesis, didn't we? If I go back here and I look at what we did in this problem, we rejected. It's really a very close call, isn't it? Because the confidence interval contains zero, but just barely. And if I was just thinking of the confidence intervals, I might actually have cause to accept this null hypothesis. So here's an interesting statement. Depending on which version of the test you do, you can get a different answer. With the same numbers and the same information. Looking at this problem two different ways, I've got two different answers. So maybe 0.01 is too sensitive for this test. Really, I think what it comes down to is the way these populations vary. And looking at our variance might actually help us a bit. So we'll talk about comparing variances when we get back from Easter. So I hope you'll have a wonderful break. I will see you all a week from today.